Okay, so welcome back. We're doing lesson 3 today, types of energy and conservation of energy. For those of you who have me before, you know that I do like to review the lessons from before. So at this point, I want you to pause the video, take out a scrap sheet of paper, your calculator, do some work on trying out this question, and then what I will do is I'll actually take it up with you in a little bit when you're done. Okay, so pause the video, try out the question, okay, and then I'll take it up. So a ball of mass of 52 grams is thrown from a height of 3.5 meters above the ground. They want you to calculate the gravitational potential energy. So hopefully the first thing you know is that your mass, make sure you convert it into SI unit, so kilogram. So to do that, you have to divide it by 1,000 to go from grams to kilogram. And they gave you that the height is 3.5 meters. And the first question asked for calculate the gravitational potential energy. So the equation for gravitational potential energy is mg times h. So mass is 0.052 times 9.8 times the height, which is 3.5. So do your math. So I got the answer to be 1.7836, and that's in joules. And look at the question, there's 2 sigdics, so I'm going to round it to 1.8 joules. Okay, part B, calculate the gravitational potential energy when the ball is 2 meters above the ground. So now your height has changed. So same given as before for the mass. The only thing is that your height has now changed. So EG equals to MGH. Sorry, I'm squishing the space. So 0.052 times 9.8 times the height, which is now 2 in this case. So 1.0192, so rounded to 2 sigdics, 1.0 joules. So the last one is basically leading to this lesson is if those missing energy has been converted into kinetic energy, they want you to calculate the speed of the ball when it's 2 meters above the ground. So we started off at a point that is higher. The height was 3.5 and the ball was dropped. And they are basically assuming that the speed at the top of the flight when you are just dropping it at 3.5 was a drop with 0 meters per second. And they're basically asking you if the height is 0, what would the speed be now? Okay, so at the beginning we got the 1.8 and then now I have 1.0. So the change, they're telling you the missing energy, meaning the change in gravitational potential energy has now been all converted to kinetic. So I'm going to first of all work out the changes first. So I got the answer. I'm just going to use all the value. As you know, I like to keep them as accurate as I could. So I had the initial energy is 1.7836 minus the at 2 meters what the potential energy is. So the change in energy is 0.7644 joules, and they're telling you that they have all been converted into kinetic energy. And I know that the equation for kinetic energy is 1/2 mv squared. And they're saying that all of the 0.6.7 is now converted to kinetic energy. So I'm going to convert it and plug in my number, 0.052 for the mass. V squared is here. And then I rearrange the equation and solve for V. So I would first of all take my 0.7644. I would multiply it by 2. You can divide it by half if you want. And then I would divide it by 0.052. And then take the square root of it because it's the v square. So I calculated that the the speed at that time would become 5.4 meters per second. So we're going to first of all talk about the different types of energy. The first one is called mechanical energy. We already mentioned at lesson 3, basically it's the total energy, and we will be basically our whole conservation of energy lesson has to do with this. The total mechanical energy, I'm just going to say ET for now. It's the sum of the two energy that we've been talking about, the kinetic energy and the gravitational potential energy. And so we already talked about what gravitational potential energy is. So gravitational is when it's affected by the force of gravity. So if you lift something high up, it is going to store that energy. Radiant energy is light. Electrical energy, there's two types. There's static and current electricity. We've covered that in grade 9. Thermal energies is heat. Sound energy is sound because of the oscillating of atoms and particles. Nuclear energy are atomic energy that are being stored by protons and the nucleus. Elastic energy are also called a spring energy. So if I have an elastic or a spring, and when I stretch it, I'm storing energy. And when I let go, I can fire the elastic at you and it's going to hurt. Finally, is the chemical energy, which is also a stored type of energy. It can be in food, in fuel, in molecule. Battery is an example of a chemical energy. So some sort of thing that we could be talking about are these things called the energy transformation equation. I just want to do one really quick example so that you can get an idea of what we will be talking about is when we talked about the conservation of energy. Okay, energy is transformed from one to another. So say for example, if we want to talk about a flashlight. Okay, the flashlight is first of all started off with the battery. Inside the battery, there is chemical energy that is being stored. And that chemical energy, when you put it in, you hook up the circuit, what happens is it's going to turn into electrical energy. Electrons is going to start to flow. It's actually a type of current, electrical current energy. And when that happens, what happens is it then turns into two types of energy, which is the radiant, the light energy, which is what you want. And the other one, it's pretty much everywhere. In grade 9, we talked about basically frictions or wasted energy as heat. So this is an example of energy transformation equation. And now, in particularly, we're going to talk about a law that is very important, okay? There is this law called the law of conservation of energy. The light from the flashlight didn't come from nowhere. It has to come from stored energy, and your battery can be used up, right? Like you have to charge up your battery, and we're not going to go into detail of how it works, but it's going from one form of energy into another. And so in an energy transformation, what happened is the total amount of energy is the same. It just changed from one form to another. So this is an important law in physics. Law of conservation of energy. Energy is neither created or destroyed. What happened is it transformed from one form into another, and no energy is ever lost. So that's why we say EA equals to EB. And this is important. This is something that you would write and get 1 mark on every single question that you know is involved in law of conservation of energy. So this is the equation to talk about the total mechanical energy. It's potential plus kinetic. And since we learned that potential is mgh and kinetic is half mv squared, that's why they throw that into there. So they wanted you to consider a situation. I'm actually going to label them off. This is case 1. Okay, so I'm just going to call this A. Okay, what happened is it's telling you that you have a 65 kilogram diver on a 10 meters platform at the top of the platform. So at this point, we got this person. So this platform is 10 meters tall. Okay, so he's at a height of 10. So you got this guy here. Okay, we call this EA, total energy at A. And it is going to be composed of gravitational and kinetic energy. And because he's just standing on there, your kinetic energy is 0. That's where this came from. So that's why they're saying at the top of the platform, it's all gravitational potential. Then we're going to go to this. It's the same situation, but now the diver, instead of being 10 meters above, he has now fallen 5 meters. So if I were to call this situation B, okay, I'm going to say that this guy is now right here and he is falling down, diving down. We're going to call this EB, and he's now at a height of 5 meters. And does it make sense that he would have speed up a little bit? So I didn't write it down at the top here, but at the top, the velocity is 0. That's why I can cancel the EK and call it the 0. At the bottom, at the middle, I still have some potential energy, but at the same time, I still have some speed. We haven't worked out what the velocity is yet or what the speed is yet, but does it make sense that he would have sped up from the 0? He's no longer going at 0. So the total energy is going to be some potential and some kinetic. And then the story goes on. We are now he has reached the surface of the water. So he is now, I'm going to call this situation C. He's now right at the surface of the water. Okay, so the height is now 0, right? Because he's at the lowest point. We always have the reference point to the question as being the lowest point. I don't know what the speed is, but what I do know is that if I compare the speed, does it make sense that the bottom should be the fastest? Because now it has fallen for the longest time. And the other reason why we could explain why the speed is the fastest is that because now the gravitational and the kinetic energy, the gravitational energy is 0 because my height is 0. So that means all of the energy that we started off with has now been converted into kinetic energy. Okay, so that's what they're trying to tell you. Okay. And if you were to do the math, EA should equals to EB should equals to EC. The kinetic energy, the total mechanical energy is the same within the system. And we call this a closed system because I didn't in there start pushing him a bit more or whatever. Okay? And so the law of conservation of energy is telling you that all of these plus any other point along the system, no matter where I am along the system, my total energy always have to be the same. But it just might be a different ratio of what form it is in. Okay? So to start these types of questions, you will always pick a point that you would have both the height and the velocity to be at least one of your points so that you can solve for something else. Okay, so let's finish this question and take a look at the actual example that they want you to do. Okay, so it's a continuation of the question just now, and I'm going to show you the proper format of how you would need to show all the work to get all the proper format and the marks and stuff like that. Okay, so they're asking you to calculate the speed after it's fallen 5 meters, and then just as it reached the water. So basically, they would like you to calculate what is the speed at point B and point C of what we were talking about just now. So I'm going to redraw the picture. Okay, this is my point A. Point A is when he was at a height of 10 and a speed of 0. So that's what we were given from the beginning. If you need to reread the question, you're totally welcome to do that. Okay, and they would like you to find out at point B what is the speed when it is that. So I'm just going to do this first. So this is the part that's done in blue. Okay, so at 5 meters. So this is how you would start. Because of conservation of energy, I know that EA equals to EB. Oops, EB, capital B. Okay, the things that are on the side, I honestly don't need you to write it out every time, but I'm just going to show you on the side of the thinking. Since I know that the total energy is always EG plus EK, and since I know that EG is mgh and EK is 1/2 mv squared. So from lesson 2, I'm going to put this all into the equation where EA equals to EB. So remember these, I honestly don't really need you to write it out, but I'm just showing you how I go from this one step to another. Okay, and then another thing that would be nice is see how like don't draw this down. I can split it up as long as I carefully write out what's my A and what's my B. I don't need you to write out all the, I don't need you to write prefix for every single one of them. So I'm going to show you how I would do that. Okay, so I know EA equals to EB, and because of what we wrote at the side here, I know that EA is also MGH plus 1/2 MV squared, and is equals to MGH plus 1/2 MV squared, because the potential energy and the gravitational energy adds to the total energy. So this is where I'm starting. So I will need you to write this one down. So 1 mark for writing out EA equals to EB. 1 mark for telling me that each of the total energy are always potential plus kinetic. Now I can start plugging in numbers. Okay, so I didn't write it down, but from the previous question, I believe they said that the mass was 65. Okay, sigdic is not the nicest. I'm going to change the sigdic to 10.0. Okay, so I'm just going to change the sigdic to the question. I apologize for that. And then I'm also going to change the sigdic to this to be 5.0. Okay, so now I'm just going to plug things in. I also know mass is 65 from before. So I'm going to start throwing numbers in and crossing things out that are not needed. Okay, so every time when there are zeros, this is part A. If speed is 0, do you see that the term for the 1/2 mv squared for A is gone? So this is equal to 0. So I can cross that out. But the other ones are not 0, so I cannot cross it out anymore. So now I'm going to plug in my mass and everything. So the mass is 65. G is 9.8. And the height, I just go back to here. Look at the height is 10. It has to equals to 65 times 9.8 times 5, adding 1/2. Mass is 65. I don't know what V3 is, so I'm going to leave that as an unknown. So expand it out, solve for it. So I'm just going to show the lengthy methods of doing it. So anything in green right now, if you can do it all in your calculator, you don't have to show it out. But I'm just going to write it out to make sure everybody's on board. So I'm going to multiply this out and work out what the total is. So 65 times 9.8 times 10. So this equals to 6370. It equals to, then the next part, I'm going to multiply this one out. 65 times 9.8 times 5. 3185, adding 0.5 times 65. So 32.5 V squared. I need to first of all move this over by subtracting. So 6370 minus the 3185. So I got 3185 equals to 32.5 V squared. Then I need to divide both sides by the 32.5. So 98 equals to V squared. So to solve for the V, then I need to take the root of everything. And this would work out to be 9.8994. So we would round it to 2 sigdic, so 9.9 meters per second. So the speed when it is at B is 9.9 meters. Okay, so going back to this part where I said you don't have to show anything in the green. If you're good with your calculator and you understand your math, you could punch it all in one shot, because you know that you need to subtract this number on the other side. So you really could have started with the 65.68. I'm going to undo so you know which part I'm talking about. So I am now right here. You could have punched 65 times 9.8 times 10 minus 65 times 9.8 times 5 equals, and then times it by 2, divided by 65 equals, and then take the square root. if you can't do it in one shot, definitely write it out. It's not worth losing the mark because you can't show the work. Okay, so this is done with the one with the 5 meters. So we're now going to move on and work on the one when he reaches the water. I'm going to start the question over again, just so that we're good with repeating the question and know the format and everything. Okay, so I'm going to repeat the question. I know that this guy started at the top at 10 meters at a speed of 0. I know that at the bottom, I'm going to call this point C. At the bottom, the height is 0 and the speed is what I'm looking for. As long as I have a point that I have both of the value, you can use it as one point. So if you choose to want to say EB equals to EC, be my guest. It's totally doable. But I'm just going to leave it as A and C just because A was given. It's not a calculated one, so I know for sure it's right. So remember what I said. You always start off with EA equals to EB. This is the equation to tell me, oh, I know this is a conservation of energy question. And you're going to start off and write down that on each side. I know this is repetitive, but I need you to write this out every single time for your full mark, okay? So I'm going to say this again. You can't just write 1 half mv squared equals mgh. I know those things cancel and there are zeros and stuff. You still always must show this line, okay? You must show these two lines to get your full mark. Okay, because I know it does cancel later on because the speed at A is 0, the speed at A is 0. And the height at C is 0, the height at Z is 0. I know they cancel, but you can't just go from EA equals EB and then the next line MGH equals half MV squared because you need to tell me how did you get that? You get that because you sub in a 0. You must show the full work. Okay, so after that, the other thing I wanted you to look at is, I know I didn't write the mass. I know the mass is 65. But do you have to have the mass? Do you see how you have mgh plus equals 1 half mv squared? You actually could also cancel the mass. Okay? So to make it really fast, so now I'm just going to write in my numbers. So I actually only have 9.8 times 10 equals 1 half v squared answer 14 meters per second. So keep in mind, canceling is when it's in every single term. Okay, so m was in every single term, I can cancel them. If I have cases that say if I tell you 2500 equals 1 half mv squared plus mgh, you're not allowed to cancel it because I don't have an m with the 2500, right? So only if I, like, say if I have equals 1 half mv squared, say here, when there's m and m and m in every single term, yep, m and m and m and m, I can cancel that. But if it's like a number, if it's not in every single term, I cannot cancel it. Okay, so just be careful with that. Okay, so last example. Actually, I don't know if it's the last example, but let's keep working. Okay, gymnasts of a mass of 45 kilograms have a velocity of 1.1 meters per second when he is 1.8 meters above a trampoline bed. What is the speed of the gymnast the instant before he lands on the trampoline? Okay, so I'm just going to redraw the picture. Point A is when he is at the high point at 1.8 meters. They tell you that at 1.8 meters, the speed that he was having is 1.1 meters per second. And they would like you to calculate the speed right before it lands on the trampoline, which is the height equals to 0. This is point B. If I have been nagging and repetitive, you know that you are writing the exact same line to start out. EA equals EB. I'm actually going to do it closer to the bottom so it gives me a bit more room. So EA equals to EB. And I know EA has potential and kinetic. Potential is mgh. Kinetic is 1 half mv squared. And I know that at point B, I also have potential, which is mgh, and also have kinetic 1 half mv squared. Cross off anything that are 0. So I see h is 0 at point B. If H is 0 and point B, that means the whole MGH term is gone. I see mass in every single term. I can cross those out as well. Let's see what I have left now. Okay, G is 9.8. Height at A, I look at the picture, which is 1.8. Adding half, the V is 1.1 square, equals to, the MGX term is gone, so I now only have the last term, so 1/2 V square. Punch the left side into the calculator, times it by 2. And then take the square root. So I got the answer to be 6.0469 sig digs. So the answer worked out to be 6.0 meters per second. If you haven't been pausing any of these questions, may I suggest you pause and do it. Oh, actually, you know what? This will make it a bit more hard. But I can do this with you. Okay, you can pause later on. Okay, a 17 kilogram child is playing on a 2 meters long swing. The child swing high enough to make a 45-degree angle with the vertical. What is the potential energy at the maximum height, and what is the maximum speed? So you got a child swinging, and the swing itself is 2 meters long. So if this is the starting of the string, if I tell you that this, I'm going to try to draw it better. Let's do this one. Okay, so I'm going to do a line, and this is a 45 degrees line, and they tell me that the length is 2.0 meters long. And they make an angle of 45 degree with the vertical, so that line goes like that. And then the child is right here, and the child swing and get down to the bottom and then keep going up, right? So they're asking you, what is the potential energy at the maximum height? The maximum height is right here. And in order, I'm going to call this point A. In order to calculate that height, the potential energy, I need to first of all work out what the height is. And this question looks really tricky. And I would love to challenge you. I'm not going to talk at this point. I need you to visualize this swing. At which point are you having the maximum speed? At which point are you having the minimum speed? Okay, hopefully you got that the maximum speed should be at the lowest point. Are you okay that this is your maximum speed? Because if the swing keep going, it's going to start slowing down again, right? So the maximum speed is actually at the lowest point. So at this point, point B, this is where the maximum speed is, okay? I don't know what it is. I'm just going to make a little note. This is my maximum speed. And I know from doing the couple of previous questions, I know that each of the point, I will need an H and a V. I'm going to write them down. I'm going to decide what they are. The height at the lowest point is always height equals to 0. So we're going to make an assumption that the height at the bottom is 0. I'm just going to change the color. So the height where we set the maximum speed, meaning when the child is at the lowest point, the height is 0. How do I figure out the height at the top? Once again, I would love to have you, this is when I would walk around the class and have you try to work out what is the height at point A. Okay, but I'm just going to keep going. If you want that challenge, try it out, to see if you can do it. Okay, the height is 0 at the bottom. And you might miss this. It is common sense. The swing itself is 2 meters. So it's like the rope thing, the 2 meters long swing. And when it's swinging to the side versus when it's swinging at the bottom, what you also do know is that if I actually draw a line here, this is the same swing, meaning this also is 2 meters. Are we okay with that? This is probably the part that people miss the most. Okay, if I know the height is at the 0 at the bottom at point B, and I know that even though I lift my swing and it's 2 meters long, when it's at the bottom, it is still 2 meters long. Okay, so now I'm going to draw a couple of lines just to see if I can make sense out of it. So I'm just going to make some dotted line. This is the point that is useful for you. Okay, make this equals to 90 degrees. My whole length on one side is 2. Meaning, if I can take advantage of the triangle. This is a right angle triangle, right? So let's take a look at this. If this is a right angle triangle, okay? I know this is 2 meters. I know this angle is 45. Can you figure out this side? Remember your component? Okay, this side is going to be, if you want, I'm just going to show you the full work. So I know that this is angle 90. Opposite to the 90, the 2 meters is your hypotenuse. And if this angle 45 is my angle theta, the one beside it is the adjacent. And we're dealing with cosine again. So I know cos of 45 is going to be adjacent over the hypotenuse, which is 2. The adjacent is 2 times cosine of 45. So basically the x component. Like we've been dealing with components when we did the kinematics, like vector types of question. So let's put it back now, okay? I need height to be 0. I need to work out what is the height as point A. I know the whole length is 2, but I also do know that this part is 2 cosine of 45. And I need to figure out what is the height right there from 0 to point A. So that part is going to have to be the total 2 meters minus 2 cosine of 45. Okay, so let's redraw this. There's so much picture, very confusing and stuff. So I'm just going to redraw the picture just to make it all clean. Okay, this is point A. The height is 2 minus 2 cosine of theta. Okay, I'm not making this better. So at this point, this is point A. The speed at point A is 0 because I was lifting it up, and that's the maximum height that they were getting at 45 degrees. So this is still my 45 degrees, but at this point I don't need it. Okay, the height we already worked out is 2 minus 2 cosine of 45. So punch it in the calculator. It should become somewhere around 0.59 meters. And then at the bottom, the height is equals to 0. What is the speed? Okay, so part A would like you to find out what is the potential energy at point A. That is where your maximum potential energy is. Okay, I know the equation EG is mgh. So M is 17 kilogram. So 17 times 9.8 times 0.59. So 2 minus 2 cos theta. 97.59. So the gravitational potential energy at this point is 98 joules. Okay? And then they ask you what is the maximum speed, and we already talked about that. Maximum speed is at point B at the lowest point. Okay? EA equals EB and mgh, so it's potential, adding kinetic, mgh plus 1/2 mv squared. So it's the same type of question that we have been doing from before. Crossed out any zeros. I know at point A, the speed is 0. So at point A, I can cancel the number that has the speed. At point B, which I didn't write down point B, at point B, the height is 0. So at point B, I can cross out the mgh. And I got 2 terms left, m on both, so I'm going to cancel them. And I'm going to plug in numbers. So I got g is 9.8 times the height, which we got from before, it's 0.59, equals to 1/2 v squared, and we solve for our v. So that times 2, take the root. So I got speed to be 1.082, so 2 sigdigs, 1.1 meters per second. Okay, clarification. Because of the distance learning, we usually do include these in the assessment for grade 11. But any of these types of questions, we call them the pendulum. So with this equation, 3, if you get it, that's great, okay? But we're going to be focused on it in grade 12. So at this point, you're not going to be really doing a lot of work involving them. And if you don't get it, it's okay, right? It is a very initial encounter to it, and we're probably not going to worry about it during the distance learning just because it's very difficult for you to ask questions and for me to redo it. So basically, your expectation for this at this point, rounding out the end of conservation of energy, is you need to understand work is force time displacement. If it's on an angle, you do a cosine of theta. You know that the work is change in energy, either the change in kinetic energy or the change in potential energy. You also need to know the equations separately for kinetic and potential energy and how to work them out. Sometimes we ask you to rearrange the equation for V. Sometimes we ask for mass. We expect you to be able to also recognize the SI unit for mass is kilogram. And then today is the kind of roundup for these types of energy. It's the conservation of energy. So please make sure you keep in mind that you follow the success criteria, right? So you always start off with conservation of energy with EA equals to EB, and then you plug in your potential and kinetic. The format is very similar. And so that's kind of the end of the energy types of expectation, right? Pendulum question, the one that it gets to question 3, will not be the focus. You will not be assessed on them, okay? But if you take grade 12, that would be something that we would definitely, cover, and we'll go through them again. Okay, so start working on your problem set. You should be able to finish your problem set by now. Okay, but try the homework question for lesson 3 first. Check your answers that we provided for you. If there's a question, let us know and work on your problem set.